Particle physics scientists have discovered evidence that there could be a whole new physics that would completely turn our understanding of the universe upside down. In this video, you will learn everything about this possible physical revolution. So stay tuned until the end. And if you like it, I would really appreciate a thumbs up and a comment, as that helps the YouTube algorithm show this video to more people. Thank you very much, everyone, and welcome. Fermilab in Illinois, USA is a research facility that primarily serves fundamental physics research. One could say that here, the smallest particles are brought together for collision to understand the fundamentals of our physical reality. For when we find out how the smallest elementary particles interact with each other, that is the key to understanding how the universe as a whole actually works. But how does this happen exactly? How do you make particles collide, and what insights can you draw from that? To study the interaction between elementary particles, huge particle accelerators are needed. Until 2011, the Tevatron particle accelerator, which was 6 kilometers in size, was used for this purpose at Fermilab. In these large facilities, particles can be accelerated to almost the speed of light and made to collide. In the Tevatron, mainly protons and antiprotons were made to collide. But how do you actually measure the effect when two particles collide? To answer this question, a large number of so-called particle detectors are installed in particle accelerators, which can measure the trajectory of the colliding particles. The trajectory allows conclusions to be drawn about the effect of the collision, and in particular, about which new particles may have been created by the collision. In principle, the results of such particle collisions are always consistent with the so-called standard model of physics. The standard model is, in principle, the totality of the findings that we today consider to be correct with regard to the physics of elementary particles. Above all, it describes the elementary particles known to us, i.e. the smallest building blocks of matter, and their interactions, in particular the strong, weak, and electromagnetic interactions. If the standard model turns out to be flawed, we would have to question all our assumptions about the cosmos. And why exactly do particle physicists believe that the Fermilab data could shake the standard model of physics? From particle decays in the Tevatron accelerator, physicists at Fermilab have remeasured the mass of the W-Boson as accurately as never before. One might now naively ask, what the hell is a W-Boson? A W-Boson is an elementary particle, one of the smallest known building blocks of matter. The W-Boson is responsible for the so-called charged currents of the weak interaction, one of the fundamental interactions in physics. However, the W-Boson is not a normal elementary particle. In contrast to the elementary particles, for example, of which you or everything you know is composed, it is a so-called gauge boson. This means that it only appears in high-energy experiments in particle physics and not in normal everyday life. That makes sense because I have never seen a W-Boson flying by in everyday life. Okay, so let's note that the W-Boson is an elementary particle that mediates the weak interaction, which is one of the 4 fundamental forces of physics. It is a gauge boson, one of the fundamental forces of physics in the year 2001. According to the standard model of physics, a W-Boson has a certain mass, namely about 80 times the mass of a proton, which is a positively charged elementary particle. But now, the unexpected. The evaluations of the experiments at Fermilab have yielded a different mass for the W-Boson. It is therefore significantly heavier than theory would suggest. It may not sound particularly spectacular at first, but that would mean that the standard model of physics is wrong. And if the standard model of physics is wrong, then it would essentially affect all our assumptions about the laws of nature of the cosmos. The mass of the tiny W-Boson thus has a massive impact on our understanding of the entire vast cosmos. The measurements at Fermilab are based on data from the already mentioned Tevatron particle accelerator, in which protons and antiprotons are brought to collision at high speed. And in these collisions, W-bosons are produced, which shortly decay into either an electron and a neutrino or a muon and a neutrino. Explaining the details of these particles would exceed the length of the video. It is also important that the mass of the W-boson can be determined from the flight direction and energy of these decay products. And the result of the researchers, the W-boson has a mass of 80.43 mega-electron volts. However, it should weigh only 80.357 mega-electron volts according to the standard model. I always feel the same way when I step on the scale. I should actually weigh only 85 kilos, but I weigh a little more. So how can this be explained? Perhaps it is just a measurement error. Unlikely, because the physicist's data is based on 4.2 million such particle decays at the Tevatron accelerator, which were recorded between 2001 and 2011. The involved physicist Ashutosh Kotwal comments on this.
This data set is 4 times larger than in previous measurements and has twice the statistical accuracy. We have subjected our result to an enormous amount of checks and tests.
There is also considerable evidence suggesting that there is no measurement error, but rather that the physical standard model is indeed incomplete. This does not necessarily mean that all our physical assumptions are wrong.
But it probably means that there are still unknown physical processes, perhaps as yet undiscovered elementary particles, and that the standard model needs to be expanded or adapted. It could also mean that there are still undiscovered interactions at the subatomic level.
Those that influence the boson and lead to unexpected results. So far, such measurement results that call the standard model into question have always turned out to be incorrect or due to measurement errors at some point. But this time it seems that the physical standard model is in real danger for the first time. Physicist and spokesperson for Fermilab David Tobeck says,
if the discrepancies between the expected and measured values are due to a new particle or an as yet unknown subatomic interaction, then there is a good chance that they will be discovered in future experiments.
For me, this is just another indication of how little we actually know about the laws of nature and the cosmos and how much there is still to discover.
And speaking of discoveries, this one is pretty scary and could cause a huge asteroid to hit Earth. NASA has overlooked something in its calculations, and it could now be that the asteroid Apophis will hit Earth after all. You can find out all about it in the video below, and if you want to support the channel, feel free to check out the older videos. Every click really helps a lot. Otherwise, I'd say see you in the next video. Take care, guys.